Okay, due to the time constraints, I'll have to make this quick. But I have like maybe two other videos, or maybe one or two videos on my channel where I spend at least 30 minutes explaining this. So if you didn't fully get it, but if you recognize the importance of this fact that divergence is the density of flux, then please watch that one. Okay. Well, I'll be really quick here. So first, what is flux? Okay, so let's talk about flux of a region. So let's say you have this omega as a given region, and you want to talk about the flux. Oh, you have a given region and you have some vector field flowing. Okay. So let's say you have some vector field flowing through it. That vector field could be electric field that we talked about, or it could be like fluid dynamics, where it's like the velocity of the fluid particle that's moving through. Okay, in both cases you can talk about flux. In fact, it's the fluid dynamics one that's more natural, because you want to know the flow of the water, right? Yeah. So if the flux is positive, then in this domain, the water levels will be decreasing, right? Because you have more water flowing out of that region. Okay. Now, if flux is negative, then more things will be coming in, right? So, if you're given a vector field F over a region omega, then the flux of vector field F on this domain omega is defined as follows. You take you go around the boundary of the omega, and then you do a dot product between the F with the outward normal vector. So this one is unit outward normal vector. And what you're really doing is, if you have a unit, you know what a unit vector is? It's size 1 vector. If you have a size 1 vector and if you do a dot product with a vector, it gives you the component of the vector in that direction. So if you have like a vector and you have this unit vector u, then it basically projects it down to that direction, and says this much is the component in the u direction. So what you're doing is, you take these vectors and here's the unit vector that's perpendicular to the normal means perpendicular. Okay, so it's perpendicular to this boundary. So you're basically taking this vector and projecting and figuring out only the component that's used to escape the region. Okay, see, if you have a region and all the vector fields are just going like that, what's the flux? It should be 0, because nothing is escaping or coming in, right? This will be 0 flux. So the tangential component of the vector fields don't do anything to the flux. Okay? You only want to measure how much is escaping. If this quantity is positive, then it will be escaping. If this is negative, then it must be going in. Negative is like when you have a bigger than 90-degree angle between the two vectors. So the vectors will be going into the region. Okay.
Yeah, it's not z-axis. It's just a proportion. Sorry. I mean, 90-degree with the x or y, right? And outward.
Yeah, the two vectors. If you're doing a dot product,
perpendicular.
If two things are perpendicular, the dot product is 0. If two things have more than 90 degrees, then the dot product is negative. If it's less than 90 degrees, it's positive.
Yeah.
So you do that, and you add up this going around the circle. So ds is S is a small infinitesimal arc element. So you're taking these quantities and you're adding them up. Okay. So that's called the flux. Okay. Now, there's a very interesting property of the flux, which is that if you have two domains, omega 1 and omega 2, then the flux of f over this omega 1 plus the flux of f over omega 2 is going to be equal to the flux of f over omega 1 union omega 2. Why is that? Well, look, if you go around like that, the outward normal over here are pointing to the right, right? But if you go around like that, the outward normal here would be pointing left. They're both unit vectors, just exactly the opposite signs. So the f dot n1, let's call this n1, and the other one going that way, we n2. F dot n1 and f dot n2 will be exactly the same quantity, just opposite signs. So if you add them up over here, it's going to cancel out, and you end up with an integral over this boundary, which is the flux around the total region. Does that make sense? Right. Now what that means is that this quantity called flux is additive. It's an additive quantity, and that's very important in physics. Like in physics, many tangible things that we can measure are additive, right? So if you have mass of one thing and mass of another one, you add them up, it's additive, right? Area, volume, these are additive, right? Yeah. So you can add them, that's important. Now, if something is additive, what you can do is it allows you to define what's called the density. You can see this definition itself doesn't seem like it's a quantity that's spread out over the entire thing. It just seems to be depending on the curve of the boundary, right? But if once you get this, if you see this, and then you can say, oh, so you can see that there's a one-to-one correspondence between, if you give me a region, there's a flux, give me another region, there's a flux, and it's additive over another one. So you can think of flux as not attributed to the boundary, but actually to the entire region. Does that make sense? And what you do is you can take any domain and you can just divide this into very, very tiny ones, and you can talk about flux around a very small region and take the density of it. Okay, so in physics, there's something called sigma, which is the surface density. Usually, you define density as mass over volume, right? But if you have a flat laminar object, you take the mass divided by the area, because it's like very flat. You don't talk about the volume. Right? So you can talk about the surface density of flux. Okay, over each region, and then if you take the surface density of the flux and multiply by the area, and you add them up, you recover the entire flux of the entire thing. Okay? So how is surface density of flux defined? Well, it's defined like this. You divide that flux, which is the integral of f dot n ds, right? Boundary of omega, and you divide it by its area of the omega. Okay. And if it's a constant density, then you can just take that this is a constant value, then you multiply that to the entire area, you recover the entire thing. But often what happens is that this is a number that varies from location to location. So there needs a quantity that we have to define for each location. How do you talk about density at a point? How would you do a density at a point? You take the limit, area going to 0. You just shrink the area down to 0, and that gives you density at a point. Okay? And that's what divergence is going to be. So here's our claim, which I want to prove. So what I want to prove is that if you take, let's say, f is uxy, vxy, and then let's say here's x comma y, and you have a very small box of size h by h. Okay? And what I want to do is I want to take the limit of h going to 0 of going around the boundary of the box f dot n ds, and you divide by h squared, you get 0. Okay. And now you get h is sent to 0. Okay. And this quantity will end up being the divergence of f. Okay. And that's not a hard calculation, but it's very long, so I'll just have to sketch this, and I'll ask you to watch another video on my channel if you want to see the full picture. Okay. So here's what we do. We will have to talk about the boundaries of C1, C2, C3, C4. Okay. And let me just show you what happens over here. C1 is the straight line connecting x comma y. Okay, I guess by now a lot of you are bored, so let me try to ask, what's this other coordinate if you move h to the right?
X plus C1.
X plus, not 1, x plus
C1.
no, h.
Oh,
X plus h, and then
Y.
you have the same height, so it's y, right? Okay. So now let's try to parameterize this C1. C1 will be parameterized as vector RT equal to, what is it? It should be x plus th comma y, where t goes from 0 to 1. Okay? So that will give you a parameterization from 0 to 1, right? Okay. All right. And then we have to compute this over C1. So let's compute C1 f dot. And you just have to know how to compute one of them, because after that you can, it's something similar. So you have like 1, 2, 3, 4 objects, and then you have to add them up and send that limit to h to 0. Okay, so first of all, what is the outward normal vector to C1? Can you point in the air? Is it this, which one? This, right? What's that vector?
0, negative 1.
0, negative 1. So outward normal unit vector. Unit vector means size 1. Size 1 vector going down is this, right? And what's f? F is uv, right? Okay. You do a dot product between them. And then, now t goes from 0 to 1, so we can replace ds by dt. And t goes from 0 to 1. No, let's just leave it as es, and then s goes from x to x plus h. I think that's easier. X to x plus h. Okay. So now only, see, y is fixed. The y coordinate is fixed. Only x is changing. So what you really have is u s comma y plus comma v s comma y. And you're doing a dot product with 0 comma negative 1. What do you get? Dot product is x component is multiplied, which is 0, y component multiplied,
Negative v.
negative v. So this is just the interval of x to x plus h, and then you do negative v of s comma y ds. Okay. And then now I have to skip things. If you do something similar up here, it's x comma y plus h to x plus h to y plus h. So over here, it's still the x coordinate that changes, the y coordinate doesn't change. So over C3 f dot ds, what happens is that you get, it still goes from x to x plus h, and then you have, oh, this time what is the outward normal vector? Which direction? This, up, down, which one? Up. So what's the vector? 0, 1. 0, 1, right? So you're going to get positive v s y plus h ds. That's what you're going to get for the C3. Okay.
I think it's xh from sh, x plus h to x.
The thing is, so that would be true if we were doing the line integral with the vectorial dr.
Yeah.
But this is ds, whereas it's a scalar. So there, in vector calculus, you have two types of line integrals. You have a vector dot dr, where the orientation really does matter. But if you have a function, then you do function times ds, and this is not a dot product, and therefore the direction doesn't matter.
Okay.
It's always in the positive direction. Okay, so it's this second type because once you do the dot product between the two, you get a scalar function, and you do the ds, so that doesn't matter. Okay. All right, so and then you can also do this and this. These are going to create the u and negative u, right? These are going to create positive v and negative v. So now this part you have to use your imagination. What's happening once you have this plus that and divide by h squared? Well, look, this minus this, and you divide by h, is y plus h, y subtracted over h. What's that like? So see, you have h squared, right? So you can put, in here you're going to get 1 over h outside, 1 over h inside, v of s y plus h minus v of s of y ds x to x plus h, and sending h to 0. What does this one look like? Y plus h, y divided by h, you send h to 0. What's that?
1.
0. No, you have a name for it. F of x plus h minus f of x divided by h, you send h to 0. What's that called?
Oh,
Huh?
slope.
That's the derivative.
Derivative.
Yeah, that's f prime of x, right? And here, because you have x and y, you need a partial derivative. So this part will give you v differentiated by y. Okay? And then the outside should be thought as the average value. So you know that if you have b minus a, the interval length from a to b of f of t dt, this is called the average value, right? So you're taking the average value in the x direction, but you're decreasing that to 0, right? You're decreasing the interval to 0. So what does that give you? It's the average over a point. What's that? It's just the v evaluated at x. See, if you send h to 0, you're taking the average of this quantity over x. So what does this limit give you? It gives you v differentiated by y, and you plug in x and y. That's one part of the divergence. The other one, if you do these two other ones, you're going to get u minus u. This will be the negative direction. This will be positive direction. So again, you're going to get u differentiated by x from these two. So if you take that limit, the end result is that this is going to give you u differentiated by x plus v differentiated by y. What's that? That is the divergence of f. Divergence is u differentiated by x and v differentiated by y. So that's the proof. Okay?